Earlier, you calculated the force from a charged rod on a point charge. And in this video, I would like to do a very similar calculation because people had some questions about that. But I don't want to duplicate it exactly because I think we can also learn something else new from this. Okay, so what I'm going to calculate instead is the closely related quantity, the electric field from a rod. And then I don't have to worry exactly about the point charge that's involved. Okay, I'll treat that as just a test charge. Okay, so what I'm going to start with is a rod like this. Okay, and we're going to assume that it has some charge on it. Okay, and I'm just going to call that amount of charge Q. And we'll just assume it's positive to make things simple. And I'm going to assume that the charge density is uniform. So it won't matter which part of the rod we look at, the distribution of charge will be uniform. Okay, and let's say that the length of the rod is L. Okay, so what I'm going to do is I'm going to set up my coordinate system like this. And then the coordinates here are going to be, this will be L over 2, and this point will be negative L over 2. Okay, so the total length of the rod is L, and the x-axis here is going to be centered on the rod. Okay, so this distance is x. And I want to consider some specific piece of the rod. Okay, so I'm going to draw an element of the rod like this. Okay, and that rod is going to be at position y. So this length is y. And the thickness of that is going to be dy. Okay, so I need to be careful about the thickness of that element, because if it's thicker, then it'll have more charge, and if it's thinner, it'll have less charge. So that will actually go into the calculation. Okay, so this is most of what we need. All I'm going to add to this now is I'm going to give a name to the distance between this point we're interested in and the actual element of the rod we're calculating for. So I'll call that r. And I'm going to name this angle here theta. Okay, that will also be useful. Okay, so the first thing I want to do is find some relationships between the quantities in this calculation. All right, so one of the ones that I can see immediately is that r is part of a right triangle. Okay, so r has, it's the hypotenuse of a triangle whose side lengths are x and y. Okay, and you can see those x and y form a right triangle here. Okay, so that means that r is the square root of x squared plus y squared. Okay. Also, I'm going to want to use the angle there. So angle theta, and in particular, in a little bit, I'm going to want the cosine of that angle. So I'll just write that down now. So the cosine of theta is the adjacent side of that same triangle, which is x, divided by r. And we know r is square root of x squared plus y squared. Okay, so I have an expression for cosine theta. If I wanted sine theta or tangent theta, I could construct it in a similar way. Okay, so the other thing that I need to know is how much charge is in that piece dy. Okay, so there's two different ways to think about it. So the way I like to think about it is that the charge density where dy is located is going to be the charge per length. So dq is that amount of charge in the length dy, and because the rod is uniformly charged, that's going to be the same as the overall charge divided by the overall length. Okay, so we can do that. Another way to think about this is that the fraction of the charge that's in that little piece is going to be dq over q. So if 1% of the charge is in dq, then dq over q is 1%. Okay, and that's going to be the same as the fraction of the length dy that is in the total length L. Okay, so dy over L is the fraction of the length, dq over q is the fraction of the charge. Okay, so either of these give the same relationship if you just algebraically rearrange. So whichever way makes more sense to you is perfectly fine. Okay, so then at this point, we can proceed with the calculation. Okay, so first of all, the force, rather the electric field from dy, I'm going to call dE. So that's just the piece of the electric field that is due to that. And then later we'll integrate to get the total electric field. So that's just going to be given by k times the charge from that little piece, dq, over r squared. Okay, that's basically just Coulomb's law. All right, now based on symmetry, I know that the overall electric field is just going to be along the x-axis. Any vertical components will cancel because here there will be a downward component from the piece I drew, but symmetrically across the axis we'll have another component over here. And that one will have a vertical component that will be exactly equal and opposite to the one we're interested in, so those will cancel out. Okay, so what I want to do is I want to take the x component, because those are all going to be to the right, so those are all going to add up. Okay, so the x component is going to be the same thing, the same magnitude, k dq over r squared, but times cosine of theta. Okay, and in particular, we have an expression for cosine theta, and we also have an expression for r. So what I'm going to do is I'm going to plug those in. So I have k dq over r squared, which is just going to be x squared plus y squared, times cosine theta, which is x over square root of x squared plus y squared. Okay? And so then what I'm going to want to do is replace dq with something in terms of something I can integrate over. In this case, I can integrate over dy. So I'm going to make the replacement then. K dq I'm going to write as q over L dy. And then I'm going to copy down all the rest of the things that I had. So there was an x, which I'll put over here. And then underneath I have square root of x squared plus y squared times x squared plus y squared, which altogether is square root of x squared plus y squared cubed. Okay, so that's just an algebraic rearrangement. Okay, so now to get the total electric field for the whole rod, what I want to do is I want to integrate. So Ex is going to be the integral, and I am integrating over y, so the limits will be from minus L over 2 to L over 2 of that expression above. So K Q over L times X dy over square root of x squared plus y squared cubed. Okay, and at this point, that's basically it. That's the physics of the situation. From this point on, it's just doing some tricky integration, but otherwise, this is essentially the answer. Okay, so let's go through that tricky integration. Right, so essentially, whenever you see something that looks like a square root of x squared plus y squared, that's an indication that you're going to want to use the technique of doing a trig substitution. Okay, so the substitution that I want to use is going to make it so that x squared plus y squared is going to look like x squared plus x squared tangent squared of something, which I'll just call alpha. Okay, and the reason for that is because if you make that substitution, then this thing, x squared plus x squared tangent squared, becomes x squared times 1 plus tangent squared alpha. And 1 plus tangent squared alpha is secant squared. So equals x squared secant squared alpha. Okay, and since that's inside a square root, that's going to simplify nicely. All right, so what was the substitution? Well, I made the y squared into x squared alpha. So y squared equals x squared tangent squared alpha, or y equals x tangent alpha. All right, so now we know what that's going to do to the square root. We need to figure out what it'll do to the dy. Well, if I just take the derivative, dy is going to be equal to x times secant squared alpha d alpha. Okay, and that's basically it. So what I'm going to do is make that substitution. So ex is equal to the integral. And let me hold off on updating the limits. So I should do that right now, but what I'm going to do instead is I'll translate everything back into x's and y's before or after I do the integral, and so then I won't have to actually update the limits. Okay, so k q over L, x stays the same. Then for dy, I have x times secant squared alpha d alpha. And on the bottom, I'm going to have x cubed secant cubed alpha. Okay? And so that was just plugging in these two things that we calculated, the dy and the thing that's in the square root. Okay, so then I can cancel out some x's and I can cancel out some secants, and what I'm left with is k q over L d alpha over x times secant of alpha. All right, so 1 over secant alpha might look a little scary, but remember that secant of alpha is 1 over cosine alpha. So this is actually just k q over L, x on the bottom, times cosine alpha d alpha. Okay, so that's what we're integrating. Integral of cosine is just sine. kq over xl sine alpha, which we have to evaluate. Okay, so I told you I didn't want to bother updating the limits, so I either have to update the limits now when I evaluate alpha, which you can do, or I'm going to turn it back into something in terms of y's. All right, so what I'm going to do is I'm going to look back up at this relationship that I had between x, y, and alpha. And this is a general trick that you can use anytime you're trying to convert a trig function into a different trig function. Okay, so I have something about tangent alpha, but what I need is something about sine alpha. All right, so if I have a right triangle like this, and I name this side alpha, well, I know tangent of alpha is y over x. That's the definition of alpha over here. So that means that this side's y and this side's x. Okay, if I draw this triangle where this is a right angle, then that equation, y equals x tangent alpha, is true. Okay, well, using the Pythagorean theorem, I can label this side square root of x squared plus y squared. Okay, so looking at the triangle, we can see that sine alpha has to be equal to opposite over hypotenuse, which is y over square root of x squared plus y squared. Okay, so we can make that replacement now. All right, so when I do that, I'm going to get kq over xl times y over square root of x squared plus y squared, evaluated from now y equals negative L over 2 up to L over 2. Okay, so at this point, we can just plug those in. when you do that, what you'll get is K, Q, L, because you'll have L over 2 plus L over 2, over XL, square root of x squared plus y squared. The L's cancel. And then at the end of the day, you've got KQ over x square root of x squared plus y squared. All right, so this is the electric field near a line of charge or near a rod. Okay, and it should look extremely similar to the expression that you had for the force. Oh, I forgot to plug in the L over 2 for y. So what this should actually be is L squared over 4 for this part. All right, so as I was saying, this is the expression for the force on, or for the electric field from a charged rod. Your expression for the force looks just like this, except for it was the electric field times whatever test charge you had, which we didn't bother with having a test charge because we just have the electric field this time.